All right, hi guys. So, what I want to introduce you to today is GBZ80 programming. This is going to be a short tutorial to see if you get some interest in programming these older instruction set architectures. GBZ80 is an 8-bit CPU and it uses a 16-bit data bus. To program these, we can actually do this on a Windows machine. I'm running Windows 10. You can run these programs to make a Game Boy game on really any machine. There's a lot of support documentation out there, although there's kind of a lack of tutorials. So the tutorial I'm going to give you today is adapted from a free online tutorial. The link to that tutorial will be in the description. But the way that I've set this up today, I think the code might be a little easier to read and understand. So again, I've adapted it from that older tutorial. So the goal of today is to get you interested in not just programming the Game Boy, but learning a little bit about the assembly language, and maybe learning a little bit about designing artwork for the Game Boy, which is a challenge in and of itself. So with that being said, let's go ahead and get started. There are some programs you're going to need to do this. One would be any type of text editor to edit your code. If you don't have a basic text editor, I would suggest use that you like at least. I would suggest using Notepad because it's free and already comes installed on Windows 10 and many other Windows distributions, older Windows distributions. I'm going to use Notepad++. That is also free to use, and I like that because it has some additional features. So, text editor, you're also going to need the RGB DS assembler, which is actually three programs in one to do all of the assembly and linking of and fixing of your Game Boy program. So your actual executable file. So if you look here, I have RGB. If I check RGB ASM version, you can see I'm running RGB ASM version 0.5.2. Link to this in the description, as well as all of these other programs. They're free to download and fairly easy to install. There's plenty of instructions on the various pages where these programs come from that walk you through how to get things like the assembler installed, the assembly tools rather, and all these map and tile design programs. All right, so we need the assembly programs. We also need a way to design tiles. So I'm using the Game Boy Tile Designer. We also need a way to build a map from the tiles that we've made so we can actually make a background image. And then we need a way, of course, to actually see all these things. So we need a way to play our Game Boy game. So we'll just use a simple Game Boy emulator. I'm using BGB. You can use practically any Game Boy emulator, although from my understanding, BGB is one of the most accurate in terms of simulating or emulating the real hardware of a Game Boy. And it also has all these handy features like the VRAM viewer and debugger, so you can actually see what's going on under the hood while the game is running, which is really cool. So we're going to go ahead and minimize these things and just leave up our tile designer and our map builder. So first things first is we want to design some tiles. So say we want to build a mountain. I always like to leave the first tile blank. It's just easier when it loads into the map builder, but you don't need to leave the first tile blank if you don't want to. I'm going to go ahead and do that though. So we have 4 colors to pick from on our color palette: white, light gray, dark gray, and black. I'm going to pick black to start with, and I'm going to use the pen tool and just left click and go diagonal through this 8x8 pixel tile. So I'm going to do the same thing, a mirror image of this here, and I messed that up a little bit, so we're just going to erase that tile. Awesome. And we're going to make something for the ground here, so we're going to do just a straight horizontal line. And I think we're good. So now what we want to do is we want to go ahead and first save this. I already have named it mountain.gbr. You're going to save it as a GBR file. That will allow you to open this up in the Gameboy map builder. So go ahead and save that wherever you'd like. Doesn't matter. And we also need to actually export it to the actual data, the bytes that we're going to load into our program. So this is going to be exported as an assembly file. So we click export to. We're going to name this something. I think I have one saved here already called, yes, mountain.z80. We'll just do it as our RGBDS assembly file, which is just as they label it as the 80 file. You can put whatever you want for the labels. It doesn't matter. The important thing is, though, is we need to know how many tiles do we have. Well, we have 4 tiles. We want to keep that blank tile in our tile set just in case we need it. So we will include tiles 0 to 3. So we'll do from 0 to 3 and click OK. And then we'll go ahead and export it. So now that's been exported to something called mountain.z80, I believe is what we named it. And we're going to go ahead and grab the data from that in just a minute. But first things first is we're going to close out of this. Yeah, if changes were made, you can click yes and save that. And now we want to move over to our map builder program. So in our map builder program, what we want to do is go to map properties, and we want to make the width of our map 32 tiles and 18 tiles high. So if you've looked at some of the specifications for the Game Boy screen is actually 160 tiles wide by 144 tiles tall. And that works out to be, in terms of tiles, 20 tiles wide and 18 tiles tall. However, the actual viewport is reading or viewing something much larger than that. So it's actually viewing something that's 32 tiles by 18 tiles high, although you just won't see all of those tiles that are beyond column 20. So with that being said, we're just going to have all of those tiles from 0 to 19 will be our actual thing we see on the LCD screen, and then everything else from column 20 and beyond that will just be blank. But we do need to include that, otherwise our image is going to get a little bit messed up when we export the data for it. So we do want to pull up a tile set to use with this. We're going to use that one that we just made, the mountain.gbr. Go ahead and click OK. And you can see on the right-hand side here, we have the tiles that we created to draw this particular map. So we want to make like a ground for this mountain to be on. So we'll start here. Actually go all the way over to tile 19. Okay, so that's 0 to 19. That's 20 tiles wide. We're going to actually be able to see that on the LCD screen. And now let's start drawing our mountain. So we'll go ahead and draw one side of the mountain, draw another side of the mountain, and I think we are good. So awesome. We can even do like a mountain in the background too if we want, maybe a smaller mountain. Oh, I guess there's going to be a little bit of overlap there. That's fine. All right, so we have some mountains here. We have some land that the mountains are on, and we want to go ahead now and actually save this and then export the tile map so we know where all of our tiles are going to actually be placed on our screen. So first thing is we're going to save this. Save it as whatever you want. It's going to be a .gbm file. And then we're going to go ahead and go to export to. Very similar process to what we just did with the tile set. Pick a name for it. And I already had something saved previously, so we're going to overwrite it. We want to label it something. So these won't matter so much because we're just going to copy the data over to our main program. All right, but what is important is under this location format, we need to set a property. And what we want to do is set the tile number property. And we want the plane count for this to be one full plane at 8 bits. Because we have, if you saw before with the tile sets, it's 8 bits per row. So we want that to be one plane, 8 bits. If we don't do that, then it's not going to export the correct data. So once we've got that, we can OK, and we can go ahead and hit export, and then we can close out of this program. So save changes, sure. All right, so next up is to actually write the code. But before we do that, we might want to see a couple places where we saved our previous data. So we want to go into wherever you saved those tile maps and the tile sets, and you want to pull the data from those and copy them into whatever your program's going to be called. I'm calling it tutorial. It doesn't matter what you call it though. So somewhere at the bottom of your file where you're going to write your Gameboy program, you're going to want to make a section called tiles and a section called tile map, or labels for them rather. So to get your tile set data, you want to find where you saved mountain.z80, and you want to copy all the stuff that's underneath the label. So all these bytes, you're going to go ahead and copy them and paste them underneath your tile label. Now you're done with that. Same thing with mountain tile map.z80. You want to copy all of these bytes of data, go back to your program file, make a label called tile map, and paste that there as well. All right, so we've got that covered. Your data should be, your data for your tiles and your tile map should all be in your main program. Now we actually want to look at how does this program work. So I've already written the program here, but I will leave this up for you to see and copy. But I will close out this because we don't need it anymore, and I'll walk you through exactly step by step how this works and how the Gameboy converts or displays this data that we just created in these two different programs. So first things first is we want to include this hardware include file. I have this loaded up here so you can kind of just see what this is. It's kind of just a large file of constants to make it a little easier to name the memory locations and the registers that we use for various purposes. So you don't have to use that. You can just use the actual memory addresses for all of these different locations that we're going to write to and manipulate. But that can be a little hard to remember all of the important ones if you're a beginner to this like myself. So we're going to use this hardware include file to make it a little easier on ourselves. And after that, we want to leave some room for the all the like the Nintendo logo and stuff that happens in the beginning, which is required when the Game Boy boots. So we just have this kind of boilerplate section header that happens here. Then we actually get into our program. So we have an entry point, which just starts by disabling our audio. We don't want the audio driver because we're not going to use it in this program, and it requires some extra code to get working. So we're just going to disable it by sending a 0 into the accumulator, which is just a register in the GBZ80 processor. And then we send the accumulator value, which is 0, into our register for the audio driver. And when that gets set to 0, it just turns the audio driver off. And now we actually get to the game where we're going to display our our mountain image, our landscape scene that we just created. And to do that, we make some function calls to some function routines that I've created below. So really four things have to happen for the image to be drawn to the screen. Number one is we need to turn off the screen so that we gain access to the video RAM and the pixel processing unit. And to do that, we need to wait for the screen to be in V blank or vertical blank. In other words, as the LCD screen cycles through each line, there are 144 lines of pixels or rows of pixels, and once it gets past 144, it's in a blanking period for a short time. During that blanking period, you are free to write to the screen, make calls to the screen. And what we want to do is actually turn off the screen because if we try to do anything while the screen, like if we try to shut it off before it gets to the V blanking range, we can actually damage the hardware. If this is on a real Game Boy, you can actually damage the hardware. And in fact, historically, Nintendo would deny the production of any games from publishers or game developers who did not adhere to these protocols. So the code had to, the assembly code had to actually turn off the screen in a safe way, meaning it had to be turned off during this V blanking period. So we'll make that call to a routine that does that for us. Then we're going to make a call to a routine that copies all of our tile set into the video RAM. Then we're going to make a call to a routine that copies our data for the tile map to tell us where to put all of those tiles and in what order to make it show that mountain image. And then lastly, we make a call back to the LCD controller to turn the LCD back on. And then we just do an infinite loop here where we just keep jumping back to this label called done infinitely, so our image will just keep staying up on the screen and it won't go away until we close our emulator, or if this was on a real Game Boy, until we flipped the power switch. All right, so what do all these routines do, these four routines? This part here is probably maybe the most complicated because this is where we're actually writing functional routines and manipulating bits in and out of registers. I won't get into this in too much detail because the hope is that in later lessons that we can do something a bit more and study how the Game Boy actually works. But we'll go through at least the gist of what each of these routines does for now. So the VBlank routine simply checks the RLY register and checks to see if the value in that register is at 144. In other words, is it past the final line of the or final row of the Game Boy screen? If it's not, then it continues to loop through these three steps here. If it is, though, past 144 or 144 or higher, then we go down to this next small block of code where we load 0 into our register A, which is our accumulator. Then we load that value, 0 being that value, into the LCD controller, which just turns off the LCD screen. We hit return command, which brings us back up to the end of our call wait vblank. And then we go to copy tiles. Go down to copy tiles when we call this routine. And now we want to actually loop through all of our tile data that we copied down here. So this is all of our data for our tiles, our 8x8 pixel tiles. And what we do here is we load the address of tiles into the DE register. We load the address of video RAM where we want to start storing these tiles into the HL register. We're going to use address 8000. That's the start of video RAM. And then we need to know, well, how many bytes of data do we actually have? Because we need to know when to stop our copying loop. So we're going to take and put a label underneath our tile data called tiles end. And that way we can take this label tiles end and subtract the label tiles, and we'll know how many bytes of data we have in between. So we'll load that value into register BC. And once we've done that, we can actually loop through all that data, copying each byte one by one of the tile set into the video RAM starting at address 8000. And then once we have decremented register BC down to 0, in other words, we've finished all of our bytes of data, we've gone through we've looped through all of them. We are going to go ahead and end the loop and return back up to the next function call. So we do copy tile map next, go down to copy tile map, and this is essentially the exact same thing. We've again loading the address to tile map into one of the registers, loading the address to video RAM where we want to store our tile map. We're going to use 9C00. And then same trick that we used before. We want to know how many bytes of data are in the tile map. So we do tile map n minus tile map. I've made labels for those before and after all the tile map data. As you can see, tile map up here and tile map n underneath. That'll tell us how many bytes we have in between. And then we can just load that into register BC and then loop through all of our tile map data, decrementing BC every pass through the loop. And when we're done, we can return back to our final function call, which is to turn on the LCD screen. So we go down to turn on LCD screen, and we need to do a couple things here. One is when we turn on the screen, we need to tell it a few things. So we need to turn it on, and we need to tell it where does it need to view the tiles and the tile map. Along with, there's several other special things that can happen, but we're not going to deal with those today. So this 8-bit piece of data here, this byte of data, is going to tell the screen to turn on and make sure that it's viewing the tile set at register or address 8000 and tile map at address 9C00. Once we've done that, we send that to the LCD control register. And once we've done that, we need to let it know what color palette we're going to use. How are we going to color these tiles on the screen? Or how are we going to color the pixels that are in those tiles, rather. So we use this byte of data here, these 8 bits. We'll tell it to use that same color palette that we used when we were using the first program to design our tiles. We send that to the background palette register and go to return again. And lastly, we just hit this done loop and lock up and infinitely loop until we turn off the emulator, just infinitely displaying that image on the screen. Now we want to actually be able to compile or assemble this program so that we have an executable Gameboy file that we can load onto our emulator. So to do that, we're going to use our assembly tools. And I already have many of these commands and procedures already written out, so I will shortcut here, but you can copy what I've written on screen to follow along. We'll make an object file, and then we'll use the linker to link a Gameboy file. And then we have to use this RGB fix program that comes with the assembly tools to send this this 1 byte value here. So that'd be 1111 in binary. We need to send that actually into our Gameboy file to actually make it the correct size. So, and I apologize, that should be, that's a 1 byte piece of data, so that should be all ones, 8 bits of ones. So we'll go ahead and do that, and that's going to make our Gameboy ROM the correct size. Once we have that, we can see that we do indeed have a .gb file here called tutorial.gb that is 32,768 bytes total. And we can minimize this, bring up our BGB emulator. We want to go into our place that we stored the Game Boy file, and then you can just drag and drop the Game Boy executable onto the window for the emulator, and it should load. You can also right click the emulator and click open and then locate the file that way. But I think it's easier just drag and drop it. So once you've done that, you should be able to see that your image is loaded here. Now my image does look a little bit different than what we originally drew, because I actually did draw something else and copied that in here. But you can make whatever image you want. So in future lessons, what we would hope to do is, if you have an interest in maybe making some Game Boy artwork, you could make a short little Game Boy video where you scroll through a scene of different moving objects or characters or backgrounds, or in future lessons we can actually work on making a small game, such as a side scroller where we infinitely side scroll through like a landscape as a character. We might have some jumping abilities, and maybe even some other enemies that appear on the screen that we have to combat somehow. So I think this is kind of the simplest introduction, though, to the subject, is just showing you how to load an image to the screen, since, as you can see, it does require quite a bit more code in assembly than it would in a higher level language like Python or something like that, that you might have used before to make graphical based games. All right, so I hope you enjoyed this tutorial, and I hope this gets you interested in coding GBZ80 assembly. Thanks.